Hello everyone. Today we're going to be going over similar triangles and line symmetry. So let's get into it. Triangles are similar if they have the same shape but not the same size. So we encountered this a little bit last lesson. Corresponding angles are equal and corresponding sides are proportional. Alright, so let's go through a few examples. State whether each pair of triangles are similar, justify your answer. If the triangles are similar, write the similarity statement. So remember, if something is similar, we use that symbol. Okay, so we have triangle ABC and OPR. All right. All angles in a triangle add to what? It's 180, right? So if we subtract 180 by 30 and 100, what's left is 50 degrees. And similar situation here, the angles in this triangle need to add to 180, so the thing that's remaining here needs to be 30. So comparing, I've got angle B equals angle P, I've got angle A equals angle R, and angle C equals angle O. So I have two triangles of different sides, or different size, where all three angles are matched, they're equal. So therefore we can say triangle ABC is similar to triangle OPR. And the reason for that is all angles are equal, or they match up. Yeah, so I guess if we wanted to get more specific, because that could be a bit misleading, I would say angle A equals angle R, angle P equals angle B, and angle O equals angle C. That would be a little bit more precise. Whoop. A little bit more precise of a justification. Just going to resize that. Okay, moving on. We've got JKL and TVM. So I guess we've got 3 and 5 and 6 and 8. So if I want to figure out, I've got right angles, so that's great. I don't know exactly what these angles are. You'll be able to figure those out next year when you start doing trig ratios. But for now, what we can do is figure out what the missing side length for each triangle is. So to figure out for JKL, I've got one of the legs and the hypotenuse. So I need 3 squared plus KJ squared equals 5 squared. So that'll be 9 plus KJ squared equals 25. If I subtract 9 from both sides, I get KJ squared is equal to 16, and the square root of 16 is 4. So this side length is 4. Okay, so now I can make a comparison, right? So if I compare, let's go this shorter leg to this shorter leg, I need to multiply it by 2 to get from here to here. And if I compare this longer leg to this longer leg, I need to multiply by what? I multiply by 2 again. So because I multiply by 2 to get from here to here, and I multiply by 2 to get from here to here, we can say that they're similar. So we just need to multiply by 2. So the scale factor is 2. So ultimately we can say that triangle LKJ is similar to, and I should sort of, because I go from this point on the shorter side, and then I go sort of that way, so LKJ, so corresponding would be TVM. So it's triangle TVM. They're similar, and ultimately, so you'll learn more about this in a later course very likely, but we would say, well, sides are proportional. I guess that's what we have right now. Sides are proportional. But more specifically, if you want to get really technical, you can say it's through side angle side similarity. So that's a little more advanced than what we need right now. So this would be sufficient for now. But we have a side, angle, and a side, angle, side. That tells you that they're similar. Okay, moving on. Let's do. So we got DEF and BCA or BAC, whatever. So, I mean, just to look at them, they look different, but it might not necessarily be drawn to scale. So let's maybe see what we can do here. So going from, so the shortest side length here is 5, and the shortest side length here is 10. So I need to multiply by 2 to get from here to here. Okay, the second shortest side length is 6 on, try that again, 6 on DEF, and the second shortest side length here is 12 on BAC. Again, I need to multiply by 2 to get from 6 to 12. Okay, and let's see about the remaining side. The longest side on this is 7. I should multiply by 2 to get to this if they were similar, but that's not the case. So it's multiplying, so these work, right? So I multiply by 2 to get from here to there, but then I got to multiply by something else to get from here to here. So because they're not consistent, we need this all side lengths to be proportional. So we would say in this situation, triangle DEF is not proportional to triangle ABC because sides are not all proportional. 2 out of 3 isn't bad, but we need all 3 to be proportional for it to work. Okay, moving on. We've got now triangle SET and RAT. So this is a fact of parallel lines. So this line being parallel to this line, we can say that this angle is equal to this angle. So angle EST is equal to angle ART because they are corresponding. So this is a bit advanced for us right now, but maybe just take my word for it that if you have 2 parallel lines, this angle is equal to that angle. And if you're unconvinced, I guess you could maybe draw a parallel line and a transversal, and then just measure this with a protractor, and that would be sufficient. But so that's called corresponding. Next, we could say that SET and RAT, because we have a transversal here and these are parallel lines, this angle is equal to that one because those are corresponding. So SET is equal to RAT. Those are also corresponding. And last, STE and RTA are equal. So maybe just do that in a different color. So angle STE is equal to angle RTA because it's a shared or common, RAT because it is a common angle. So if we're looking at, right, this triangle, so this whole thing, triangle SET, and compare that to this triangle, RAT, those two are going to be similar because all the angles are equal. So triangle SET is similar to triangle RAT because all angles equal. So they're in proportion, right? This one equals that one, this one equals the common one, and these two are equal. So therefore, those two triangles are similar. Okay. So I guess kind of a similar thing for each pair of similar triangles, determine the length of the unknown sides. So we're told that they're similar. We need to determine the length of the unknown side. So we have X looks to be matching up with this. So 110, 110, the longest side X matches up with this one. So if you find it helpful, you can maybe just sort of color those so that you know that those are similar. And let's see, we have a Y as well, so 21 and Y. Okay, so in order for us to get from 16 to 24, I need to multiply by something. So, I mean, you can think of it as 16 times a scale factor equals 24, and we just solve for the scale factor. So divide both sides by 16, so scale factor is 1.5. So if we want to get to this triangle from this one, we multiply by 1.5. So, I mean, in the sort of words that we were using last class, we could call that model and original. So if you're more comfortable using that terminology, you can go that route. So the model 24 and the original length there 16. Anyway, we end up with the same result. So you need to multiply by 1.5 to get from this triangle to this one. And if we want to go the opposite direction, we got to undo a multiplication by 5. So that means we need to undo multiplying by 1.5. So we got to divide by 1.5. So to get from 24 to X, we need to multiply by 1.5. So we're going to go 24 centimeters times 1.5, which is 36. And if we're going from this length to that one, we need to divide by 1.5. So Y is equal to 21 centimeters divided by 1.5. And that works out to be 14 centimeters. So we figured out the missing sides, and we're done that question. Okay, so we've got sort of a different situation going on here. Again, we need to figure out the missing side. So this one because it is opposite 30, matches up with this one, which is also opposite 30, right? So you can imagine sort of rotating this about this point. So if you rotated, just sort of visualize rotating this larger triangle, keeping this one fixed. If you rotated this point down here, you'd end up kind of with something looking roughly like that, and then you could sort of shrink this down so that it links up. So this is, right, still 30. Okay, hopefully you didn't write that in pen. Okay, so 10 and x match up, and we also need to figure out what y is. So y is the longest side, looking like the longest side at least, next to 30 degrees, and that would link up with this one on the larger triangle. So I guess we need to figure out a scale factor here, and in order to determine that, we need to know two corresponding side lengths with absolute certainty. So we need to know this one, and we know that one as well. We cannot get a scale factor from these two sides because I don't know what each of these lengths is. I can't get a scale factor from this and this because I don't know what that is, but I do know that these lengths correspond. So scale factor will be something. So I guess we could go from the smaller to the larger one. So if we're going to go that direction, we need to multiply by some scale factor. This is, I guess, the model in that situation. That's the original, so because we're going from this to this. So model over original. So 21 over 12, which is 1.75. So we need to multiply by 1.75 to get from the smaller to the larger. And if we go in the other direction, we need to divide by 1.75. So therefore, x is given by 10 times 1.75. So 10 meters times 1.75 is equal to 17.5 meters. So that's the length of x. And y is given by 30 divided by 1.75 divided by 1.75, which is 17.14 meters. I can't remember if it tells us to round to anything in particular. Nope, so I can leave it to the nearest hundredth as I have here, and the 10th there is fine. Okay, moving on. So to get from here to there, so that's, so like this triangle is similar to this one. So these side lengths match up, and we just need to know how to get from this smaller triangle. So we'll do that smaller triangle to the larger one. So like this one. And like they're similar, right? Because you can take, see if I can do this. Yeah, still need one more. Right, I can take this larger triangle and shrink it, and they link up. So that shows me that they're similar. Okay, so in order for me to get from the smaller one to the larger one, I need to know two sides for sure. It's not these two because I don't know that one. But I know this bottom leg on the smaller red triangle. Scale factor, we'll call this larger green one the model, and the smaller red one the original. So it's always model over original. Okay, so I know what this leg is. That works out to be 12 millimeters. So what is the corresponding length for the model? Is it 28? So it's not quite 28, but we're on the right track. We need to actually add these two lengths together to get the equivalent side length for the green triangle. So that is 40 millimeters. So 40 divided by 12 gives us 3.3 repeating. And that's what I need to multiply 8 by to get to x. So x is going to be 8 millimeter times 3.3 repeating, which is 26.6 repeating millimeters. Okay, one more question with triangles. This is from page 350. So Tina wants to estimate the heights of two trees. For each tree she stands so that one end of her shadow coincides with one end of the shadow of the tree. Tina's friend measures the lengths of her shadow and the tree's shadow. Tina is 1.7 meters tall. Tina's shadow is 2.4 meters. And the first tree's shadow is 10.8 meters. What is the height of the tree? So we have her shadow length here is 2.4 meters. And the tree's shadow, you can see in the picture, is 10.8 meters. What's the height of the tree? So we want to figure out what this length is. Given that we have a common angle here, that angle is equal, so for this smaller triangle, kind of similar to the one that we just did. So this triangle is similar to this larger one. And we can say that they're similar because this is a right angle here. So that's a right angle. That means this is as well because they're supplementary. This plus this need to add to 180. Because this is 90, that's also 90. So that's 90, that's 90. This is a common one. That means this top angle. So let me just do, so this angle is equal to that one for both triangles. So all angles are equal, so therefore they are similar. Okay, now we need a scale factor. So we'll go from this smaller triangle to the larger one. I know this bottom leg length. So scale factor will be model divided by the original. So I'll go 10.8 meters divided by 2.4 meters. Units are the same, that's great. So 10.8 divided by 2.4 is 4.5. Unitless. And then to get to the tree length, I go 2.4 meters times 4.5 meters, or not 4.5 meters, just 4.5. And then that's 7.65 meters. So that's the answer for A. And then B, Tina's shadow is 0.8 and the second tree's shadow is 12.8. What's the height of that tree? So similar procedure. This time we have the tree shadow is 12.8 and she's 0.8. So basically same thing, same type of calculation. We do 12.8 divided by 0.8. That gives us a scale factor. This time it is 16. Okay. So the second tree height, we go 1.7 times 16, which is 27.2 meters, which is it's quite a tall tree. Okay, so that wraps it up for similar triangles. Let's move on to line symmetry. So line symmetry, a figure has line symmetry if it can be folded, so the two halves meet or match. Match would probably be a better word. The two sides are said to be congruent. So line symmetry, a line that divides a figure into two congruent parts. It is also called the line of reflection or the axis of symmetry. So if you imagine, like we've got some things here, if you imagine putting a mirror vertically, like out of the screen or out of the page here, and you set it up so that it's reflecting this stuff, if you look into this mirror, you'll see this shape replicated in the image of the mirror. So that's kind of where the reflection term comes from. A line symmetry can be horizontal, it can be vertical, and it can be, what do you figure goes there? Oblique. Moving on, polygon. Polygon is a two-dimensional closed figure with straight sides. A polygon with all sides congruent and all angles congruent. That is a regular polygon. So a few, like going through the lowest order regular polygon is a certain type of triangle. Do you remember what the name for that is? That's an equilateral triangle, one where all sides are the same. Going up one side, we've got a quadrilateral with 4 equal sides, that'd be a square. And we can continue, we'd have a regular pentagon, and this one has 6 sides. What do you figure that one's called? That would be a hexagon, so a regular hexagon if all side lengths are equal. Okay, so a few examples here. For each figure, state the number of lines of symmetry, draw the lines of symmetry, and classify each line of symmetry as horizontal, vertical, or oblique. So here we have something here. I can't split it that way, but I can split it this way. This is a vertical line of symmetry. This logo, I can split it vertically. I can't split it horizontally or obliquely because it's red on this side and blue on that side. So this is also a vertical line of symmetry. With this one, I can split that, I'll maybe do that in a different color. So I can split this one up vertically, so that's a vertical. Is there any others? Can I do oblique? Can't do oblique, but I can do a horizontal one. So it's got both horizontal and vertical line of symmetry. This one, so if I split this up vertically, so it looks almost like it could be, but imagine if there was a mirror here and this part was missing. If I saw the mirror image of this, it would look like that in the image. So it doesn't quite link up with what should be on the other side. So this doesn't have any symmetry. Same thing horizontally. If I split it up there, so this is not symmetrical. Not with line symmetry, at least. Okay, and the last one here you may recognize. So you may recognize all of these. I could do this. So this is a nice split from left to right. I could also do horizontal. So this is vertical and horizontal. Okay, moving on. Each drawing shows half of a figure where the dashed line represents a line of symmetry. Classify the line of symmetry and draw a complete version of each figure. So for this one, the line of symmetry is a horizontal one. And if I were to draw this on the reflection there, you can basically just pick a point and count the distance. So this is 3 distant from the line of symmetry. Its image will be also 3 distant from the line of symmetry, direct line. This is 1 distant from the line of symmetry. That's 1 distant. This is 1, 2, 3, 4 distant. So 1, 2, 3, 4. That's where that image will show up. That's 2. So 2. Those will overlap, and this one will go here. Okay, so draw a line from there, and then it goes there, so this will go like that, and that's straight. Then from there it goes like that, and then toward the line of symmetry to that point, then it goes horizontal like that, and then it goes back to this one. So that's a bit crudely drawn. Hopefully you have a ruler at home. Okay, this one you can go like a little bit more freehand. So it's got to be symmetric. The circle here is centered 2 from the reflection line, so it'll be kind of something like that. We'll have an X there, an X kind of centered on this line, a little bit higher, and this one is kind of 1.5 along this line, so 1.5, kind of like that. Not great, but not the worst either. The furthest point of this outside oval is 1, 2, 3, 4 and a bit. So 1, 2, 3, 4 and a bit. I'll just kind of do my best here. So like that. And it is a vertical line of symmetry. Okay, one more here. So we've got an oblique line of symmetry. So similar story. We want to make it so that each one of these points is the same distance from the line of symmetry. So this is like over there. It'll link up on the other side. So it's like midway along this line, midway along that line. Here, it's a bit, so it might be nice if you have like a ruler with you so you can measure the straight line distance between there. That'll go there. This one, so it's like, I don't know, it's kind of a bit difficult to judge. So if we kind of follow that line perpendicular, what I can do, kind of like that. So that one should be, I think, there. Yeah, okay, and then this one, it's in line with, so another way we can do it is this is in line with this point. So maybe I'll just do this in a different color. So this is 3 distant vertically, so that one will be 3 distant horizontally. Okay, and then we've got a couple more points to go through. So this one will go there, and this one will be there, and then the tip of the arrow is 2 away, so let's see, kind of running out of colors here, nicely visible yellow, so there. Okay, and then now let's just link up the points that we drew. If we were in class, I might provide you with something that would make this procedure a lot simpler. It's called a mira, or it might be 2 R's, something like that. It's basically, so if you look at it from the top, it looks like this. It's basically just like a clear piece of like plexiglass. It's red, so it's kind of convenient because you can just line this up with the line of symmetry, and if you have something drawn, for example, over here, let's actually, if it's over here, this is how you would use it. So if it's here, you'll be able to see an image if you look at this sort of from the side, and then you just kind of ultimately just trace what you see in this sort of plexiglass or acrylic type thing. Okay, one more thing I'll leave you with. Is the following picture symmetrical about any line? So maybe just have a think about that. Could it be oblique or horizontal, vertical, or at all? All right, so questions for today for you to work on, some stuff with similar triangles and some stuff with line symmetry. So that's it for the day. I'll see you next time.